Hi class, we are starting chapter 8. Chapter 8 is all about polar coordinates. We're going to start with 8.1, which is our primary discussion on polar coordinates. So what polar coordinates are is basically a new way to look at the same points that we've been working with already in what's called our rectangular coordinate system. Okay. So the rectangular coordinate system, also known as the Cartesian coordinate system, is the standard way that we plot our points and our functions on a graph. We've been doing this the entire course so far. We move over x and we move up y, right? That's a rectangular coordinate system, or also known as the Cartesian coordinate system. There are a lot of other ways of plotting the same points, okay? There's what we're going to study right now, which is polar coordinates. We have what are called cylindrical coordinates, but these are typically reserved for 3 dimensions. Spherical coordinates are also reserved for 3 dimensions. Parametric equations, which we're going to look at later on in this chapter as well. And vector equations are another way of representing points in space. Okay. So in this chapter, we're going to focus on polar coordinates, right? So instead of using x and y to get a point on the graph, we're going to use a radius and an angle, right? So let's say I have my regular rectangular coordinate system. If I want to plot a point x, y on this graph, I know that I start at the origin and I move left or right x units. Okay, so if this is the point that I want to get to, I start here. And I kind of think of these as city blocks, right? Like I can't go up the middle, so I kind of go along the edges to get to my point. So I move over left and I move over right. So I'm going to move over some amount to the x value of this point, right? And then I'm going to move upwards y units until I get to that point. And that's my point xy. That's what we've been doing so far, right? I'm sure you're very bored while I did that because we've done this so much already. But now if I want to get to the same point in terms of a radius and an angle, I still start at the origin, but I move over whatever the radius would be to get to this point. Okay, that would be my radius. And then what I'm going to do is I'm going to sweep an angle until I get to my point, right? So I move over a distance of r, and then I sweep up an angle of theta, and I still have that same length, right? So I still have r, and I sweep up until I get to the point that I want, and I move an angle of theta to get there. So I'm looking at a radius and an angle in order to get to this point, instead of saying I'm going to go over and then up, right? I go out whatever the distance is from my center to that point. That's my radius, right? I go out that amount, and then I sweep an angle upward. That's how I plot my points. Instead of x and y, it's r and theta. Okay. So again, I need a radius and I need an angle, and that's the order that they come in. Radius first, angle second. And if you notice, that's kind of what I need in order to get to this point, right? I first need to know the distance from the point to the origin, the radius. And then once I move out that distance, then I swept my angle. So first thing I need is the radius, r, and then I can figure out, and then I need the angle. Okay, so r and theta. So that order, radius first, theta second. We're used to doing everything in x and y. So obviously there's some sort of a connection between r and theta and x and y. Right? So since we're used to doing everything in x and y, it's nice to have a relationship so that we can talk about how to go from our xy coordinates into r and theta coordinates. Okay. So if I want to go from rectangular to polar, right? So I'm already in xy and I want to talk about that in polar coordinates. We need to understand that the radius is the length between the point and the origin, right? So the distance is x squared plus y squared. And it's very easy to see that as well, because you can see that it's really just the Pythagorean theorem. We saw this a lot in trigonometry, where, where we need to find the hypotenuse of this right triangle, okay? But also the distance from here to here is going to be given by x minus 0 and y minus 0, both of those squared, added together, and square rooted, right? So it's always just x squared plus y squared, square rooted. The angle is found by tan inverse of y over x. And again, that's just using the inverse trig forms, right? Because we have x and y given to us, we had to calculate the radius. So we generally want to use the values that are already given rather than values we have to calculate when trying to do any kind of math, right? So instead of doing sine inverse or cosine inverse, we're given x and y, so we'll use those values to find angle by using tan inverse. Okay. So radius is found by the distance between the point and the origin, and the angle is found by tan inverse of the height and length of the triangle. If we want to go the other way, from polar coordinates to rectangular coordinates, the relationship is that x is r cosine theta and y is r sine theta. And that should make sense as well because, again, we have our triangle, right? This is why trig is so important, because it's everywhere. So this radius is a length of r. It's not a unit value, right? So if I want to find this value, x, remember x is always cosine of this angle, but I'm also stretched by a value of r. So to find this angle, it's r times cosine of theta, which is x, right? Y is going to be the same thing. It's r times the length of y, which is always sine of theta. So those are our relationships. Our trig relationships is what helps us to go back and forth between the two forms. Okay. So polar coordinates are not unique. Okay. If I want to plot something in rectangular coordinates in x and y, I move over x, I move up y. That's it. There's only one point in rectangular coordinates that represents that point. In polar coordinates, you can have several points that represent the same point. Okay, so the form, the representation of your point is not unique. In fact, you can have an infinite ways of representing really any one point. Okay, so for example, if I want to express the point 3, negative 3 root 3 in polar coordinates 4 different ways. Okay, so these would be the most 4 basic ways, and then we can talk about how we would do it in an infinite number of ways, right? So the most basic thing that we're going to do is understand that this is my x and this is my y, right? I'm going to need r and theta. So from my x and y, I need to find r, which is the distance of this point from the origin, okay? And in order to find the angle, I will use tan inverse of y over x, right? So again, if we come back to our formulas, we're not using these formulas. We are given a point in x and y. I want to use my radius. I want to find my radius and my angle. So this is the formulas I'm going to use. Okay, too far. Okay, so to find r, I square both of these terms and I add them together and then take the square root as we're used to doing. So this is going to be 9. This is going to be 9 times 3. Okay, so that'll give me 36. Square root that is 6. Okay. Here, if I want to find tan inverse of this value, notice that these 3's will cancel out. So instead of writing just square root 3, I can write it over 1. And then I can separate these two to be over the same denominator of 2, because that tells me a nice angle that we have, right? So a root 3 over 2 over 1 over 2 gives me pi over 3 as my angle. Okay. Now the problem with this is that yes, this is the angle that's formed, but look at the point, right? The point is in quadrant 4, okay? Because the y value is negative, x value is positive. So we have to adjust this angle so that it represents the correct angle value. So we just have to subtract this from 0, okay, which is negative pi over 3. So we can write this as 5 pi over 3 if we want to talk about it in a positive angle form. And so my first way of writing this would be 5 pi over 3. So it has a radius of 6 and an angle of 5 pi over 3. Now in doing this, I found a secondary angle that I can use to represent this as well, which is negative pi over 3. So the second one is already written for me. I would use a radius of 6, and instead of 5 pi over 3, just use that negative angle, right? So really the way that I can do this an infinite number of times is just find a bunch of angles that represent negative pi over 3 and keep the radius of 6 positive. And that would always land on that point, okay? Now, let's look at a different way of doing this. Instead of having a positive 6, let's say we use a negative value of 6, okay? Well, if I use the negative value of 6 and negative pi over 3, then I would point in the opposite direction of the angle that I want, right? So I'd have to add pi to that in order to get me back into the correct direction, right? Because remember, pi is 180, that swings me back in the opposite direction. So I can use a negative radius and adjust this by going 180 degrees back into the correct direction. Okay. Now, obviously, I don't want to keep it as pi minus pi over 3, so I would do the math, and I would write this as negative 6 and 2 pi over 3. Okay, so I would go in the 2 pi over 3 direction, and then I would go in the opposite direction from my radius to bring me to 5 pi over 3. Right. So a fourth way of doing that is the same thing that I did before. Just find a second, keep negative 6, and find a secondary angle that gives me the same thing. So instead of going in the positive counterclockwise direction, I would go in the negative clockwise direction. So I would take my pi over 3 and I would add pi to that and then change its direction. And that'll give me negative 6 and negative 4 pi over 3. Okay, so I just went in the negative direction and then I changed its sign. Okay, so that's 4 different representations for the same point. Now, obviously, some of these are harder to think of than the others. Number 1 is probably number 1 or 2. Those are the ones you're going to want to stick with. Obviously, we'd probably try to keep everything positive if we can. So this is generally what you're going to be looking for your answers. Okay, but there are multiple ways to represent the same point in space when you are using polar coordinates. So let's look at an example, right? Let's find the rectangular coordinates instead for a given set of polar coordinates. So we're given polar coordinates of 2, 7 pi over 6. If I want to put these into rectangular coordinates, again, I got to understand that this is my my r and my theta. So I got to use those equations that I have. R is 2. My angle is 7 pi over 6. So in order to go in our other direction, we're using this pair of equations, right? X is r cosine theta, y is r sine theta when we're given polar and we're going into x. Okay, so r is 2, angle is 7 pi over 6, which is basically just a pi over 6, right? It's the same as negative pi over 6, basically. So we can call this, the cosine value here is square root 3 over 2 multiplied by 2, and those cancel, and then this is going to be negative because it's in quadrant 3, right? It's 1 pi over 6 over pi, so it's in the negative side. Okay, r sine theta, so that is also going to be a negative value, and it's going to have a value of 1/2 for 2 sine 7 pi over 6. But we're going to multiply that by 2, so that will actually give me a negative 1. So my point here is going to be negative root 3 and negative 1 in rectangular coordinates. Okay. So not only can we represent points in polar coordinates, right, but we can also take an equation that's already in our regular rectangular coordinates, and we can turn it into a polar equation, basically is what it's called. Okay. So we use the same substitution, right? Wherever I see x, I replace it with r cosine theta. Wherever I see y, I replace it with r sine theta. If I'm going back the other way, right? Let's say I'm given a polar equation. If I want to turn it into a rectangular equation, I use r is square root of x squared plus y squared, and that theta is tan inverse. Okay, so I use the same thing. So no matter what, whenever I'm going from one form to the other, this is my key, right? For points for equations, if I'm going from polar to rectangular, I always make these substitutions, whether it's from points or for equations. For equations or points, if I'm going from rectangular into polar, I always use these substitutions. Okay, so that's how we do that. All right, so for an example, let's convert y equals x squared into a polar equation. R is always our dependent variable, and theta is always our independent. So we're always looking for r equals something when we have a polar equation. Okay, it's always r equals something. So I want to convert y equals x squared into a polar equation. So I'm going to use these substitutions. Y is going to turn into r sine theta. X is going to turn into r cosine theta. So I'm going to make my substitutions. My x gets squared. So I'm going to go ahead and square that. So that turns into r squared cosine squared theta. And remember, r is my dependent variable, so I want to have r equals something. Okay, so I'm going to divide both sides by r, and then now I can divide by cosine squared, so I can isolate r. Okay, so I have r equals cosine squared over sine squared, and if I want, I can simplify this to cosine theta, cotangent theta. Okay, either one of these is okay as an answer. So my polar equations will always have trig functions in them. Okay. So let's do one more example. So let's go the opposite direction this time. Let's start in polar and let's try to find the equivalent rectangular equation, right? So if my polar equation is r equals 2 over 1 minus 2 cosine theta, let's find its equivalent in rectangular coordinates. So here's a disclaimer. A lot of times we're not going to be able to find the equation as y equals something. Sometimes we will, but a lot of times we won't. And that's just the nature of polar coordinates. Polar coordinates has a lot to do with circles, right? We're talking about angles and radii and things like that. So if you think about what the equation of a circle is, right? X squared plus y squared equals 1. That's an implicit equation, right? I cannot explicitly say y equals this, right? I have to have an equation where y is part of the equation. And so that's typically what's going to happen. Not always. We'll talk about the different forms and what they look like in the next section. But a lot of times we are not going to be able to say y equals this. A lot of times it's just going to be a bunch of x's and y's together. Some squared, some cubed, some, all kinds of stuff going on. So if you can't get a nice simple looking equation when you do this, going from polar to rectangular, that's fine. You're probably on the right path actually. Okay. So if I have my equation, okay, I am going to multiply both sides times 1 minus 2 cosine theta. So it looks like this, just so that it's a little bit easier for me to work with. Okay. I'll go ahead and distribute this r, right? And then I want to start to make my substitutions. So the reason I did that was because here I didn't have r cosine. I had 2 cosine. But when I move it to the other side, notice that now I have r and I have an r cosine theta. R cosine theta is the same as x. I could not replace this for x because it is not r cosine theta. It's 2 cosine theta. It doesn't work that way. I have to have that exact term, r cosine theta, to substitute my x. Now I know what r is, right? It's square root of x squared plus y squared. This is x. So I make those 2 substitutions. R is equal to this. X is here. So I have x squared plus y squared minus 2x equals 2. What I'm going to do is I can keep it like this. This is technically correct, although I wouldn't really do math or plot this as is, right? I want to get rid of this square root sign. So I'm going to isolate this term, and then by adding 2x to the other side, and then I'll square root both sides. Okay. So I'm going to add 2x to the other side of the equation. I'm going to square this and square this, and this is what I would get out. I do not need to multiply this out, right? I can keep it as is, this is a nice condensed form. I wouldn't have to do anything more than this. If you wanted to multiply this out and then set the whole thing equal to 0, you can do that. If you did do that, you might want to look at completing the square, things like that, to try to get this to look like the equation of a circle. But as it stands, this would be fine as an answer.